Okay, so today we have Dr. Hyun Jo talking about first search for an excess of electron-neutrinos in MicroBooNE. So Jay received his PhD from Yale University. He is now a postdoc here at Yale, where he's working both on the MicroBooNE experiment looking for sterile neutrinos and also on the Yale Wright experiment, part of the crystalline 100 dark matter detection experiment. He has received numerous awards for his research, including the Victor Prize in Fundamental Physics for his thesis work, and also more recently the Rising Stars in Experimental Physics at Chicago. Yeah, so if you want to go ahead and whenever you're already, I think you could just go ahead.
Okay, hopefully people can hear me fine from the remote. So yeah, thank you. You all know me, hopefully, Jay and Jay. And I, like Lauren just said, I've been working on MicroBooNE for last 3 years. And we recently released our first research on our flagship analysis, which is the search for access of electron-neutrinos in the MicroBooNE experiments, like the title said. So for those of you who already have been to the seminar last Wednesday, this may not be a surprise for you, but hopefully this will give you a bigger picture than what I gave personally at the last meeting, and try to see the where MicroBooNE is in the neutrino physics and what's the goal lie ahead. And start off with this is the beautiful event display in MicroBooNE of our signal candidate events, which I'll get to talk about later. All right, so like all the particle physics talks, start with the standard model of the particle physics, and we all know that it's been extremely successful at the predicting all the quantities of the fundamental particles. However, we also know that it's not a complete picture. There are many unsolved questions in the standard model, especially in the neutrino vectors, and that kind of starts with the neutrino oscillation. The observation of the neutrino oscillation led to the fact that the neutrino has non-zero mass, which is already out of our standard model. But apart from that, there are also many other quantities or the properties of the neutrino that could lead to beyond the standard model. And in order to prove that, we all need to look further into the measurement of all these different properties of the neutrinos, such as the masses of the neutrino, ordering of those masses, and the what's actually precise value of the delta Cp. So why the neutrino oscillation is so special? Well, all these special things about neutrino start with this neutrino oscillation, where the neutrino flavor eigenstates are not the same as the mass eigenstates. And neutrinos are actually generally produced in a flavor eigenspace, which is the combination of the three mass eigenstates. So we can see that this is the expression of how the flavor eigenstates is a superposition of the mass eigenstate, and how they are mixing together is governed by this mixing matrix right here. And this is just the flush-flow representation of how this relationship between the flavor and the mass eigenstate look like. And it has been really well-known phenomenon, as you can see from this certain simplified model of the probability of how neutrino oscillates and many different experimental observation. We have been probing this for the last 2 decades, and we know very well. But in a certain picture of these 3 neutrino oscillation, if there is only 3 neutrinos, then we know a lot about all these quantities. Like for example, in this probability equation, there are physics parameters that we can measure, like this mixing angle theta or this delta time square, and those parameters we have been measuring it with very precise, a lot of precisions. However, even with those measurements and our knowledge, there has been certain anomalies came out in this neutrino field, and there are few different anomalies, and all of them together they are all observed in short baseline neutrino experiments. So we call it short baseline anomalies. And among those, here are two of them. One is the reactor anomaly, and the other is the gallium anomaly. So these anomalies basically means that there is some discrepancy between what we observed and what we predict based on our best understanding of our neutrinos, basically 3 neutrinos. So one example of reactor anomaly, we have a lot of audience who is also familiar with this. Basically, prospect is trying to look for this, but you can see that, all these data points are actually underlined below this expected value of 1. This is the standard prediction, and all this observation is showing a certain discrepancy. Recently, there has been a lot of progress on these specific anomalies with thanks to prospect, stereo, and a lot of other experiments. And it's kind of leading towards that we also need to understand the nuclear physics and the flux of our nuclear reactors. However, this still is not completely solved yet, and people have been questioning that if this observation is the indicative of the new type of the neutrino. The other observation is the gallium from the gallium-based experiments, and when they're doing the calibration run, they found out also a deficit of the observation compared to the predicted value. So here you also can see that these data points are below what you predict in the line of the unity. And recently, the new experiments called the BEST experiments also try to see if they also can see this type of the behavior, and they recently published their result that they could also confirm that this type of the deficit still exists in their result. So this is also the same kind of question that is there a possible hint for the UV disappearing in a short baseline? The last of 3, this short baseline anomaly is the LSND and MiniBooNE anomaly, and this will be our focus today. These LSND experiments ran from 1990 to 2001. So actually the excess of the observed neutrinos over the prediction. So this is their plot. You can see that all these data points are way above their predicted value. And this gives the tension of 3.8 sigma to the prediction. And people has been trying to see what this actually means. And one of the popular theory or the hypothesis is that if we assume this new type of dispel neutrino with the mass of about 1 eV, then it could actually make up for this the excess. The MiniBooNE, they came after this LSND, try to also confirm or deny this LSND result, has also saw the excess. So this is the MiniBooNE result from the most recent paper. They've been running since 1998 and just finished running last year. Also saw this excess here. As you can see from these data points to the prediction value. And they even they have this excess of more than 4.8 sigma. And this has also certain feature. You can see that this excess is concentrated in this low energy. So people call this low energy excess or the LEE. So both experiments saw this excess, and this has not been. This has raised a lot of other theories or questions that what could this mean. One of the most popular explanation for this is try to come up with this new type of neutrino, like I said at the beginning. However, there is a certain constraints that how many active neutrino flavor there should be. There has been experiments at the lab measuring the Z width, and they are already confirmed that this weakly interacting active neutrino flavor should be 3. Also, there is a lot of the astrophysics constraints that this flavor or species of the neutrino is very close to 3. So then how can you actually assume there will be another neutrino not violating this observational constraints? Yeah, but that's how, then the solution is that we assume the neutrino, but it's not interacting as they are used to in the other neutrinos. So that's why we call it stereo neutrino. They do not interact weakly, but they only interact with the gravitational force. So that's the reason for the name of the stereo neutrino. and this will not violate these observations or the constraints. And if we do assume that, then it will actually change how the other neutrino we already know behaves. So this is the mixing matrix view that I explained earlier. So we used to only have these 3 neutrinos, and once we assume this additional neutrino, then it changes how this other neutrino also behaves, especially through the oscillation. So for example, if we rewrite the neutrino oscillation probability with the existence of this 4th neutrino, then it will become like this, and with a lot of these elements from this 4th neutrino will come into this probability. So it will change, possibly not significantly, but not non-negligibly, they will actually change how it behaves. So if we assume this extra neutrino, will this be a solution for these anomalies that we saw earlier? Unfortunately, it's not so simple. There are many different observations, and just assuming new extra neutrinos with a certain mass or its properties, then there starts to be a tension between different experimental results, also a tension between different channels. For example, how the neutrino disappears or how the neutrino appears. So there are different channels how you observe this oscillation. And just there is no just simple answer that you just assume a certain 4th neutrino with this mass will solve everything, and that's not the case. So the quest is to understand all these anomalies better and try to come up with an answer, or at least try to direct us to where to look for. So that's the point of looking for this anomaly throughout all these different stories. So going into MiniBooNE low energy access a little bit more, because this will be our focus, and this is the focus or main goal of the MicroBooNE. So looking into this, the plot that I showed you earlier a little bit more, you already see this access as a function of the neutrino energy in the at the lower energy, more or less below 600 MeV of the reconstructed neutrinos. So you can actually come up with the idea that what could this access be? This nature of this access could be either electron-like, that is coming from the electrons, or the photon-like. And we do not know which one will be, because at least from the MiniBooNE case, because the nature of the MiniBooNE is a Cherenkov detector, and for example, they are doing their identification of the particle through to looking at how the ring of the Cherenkov ring look like. And from the photons and from the electrons, they actually have very similar rings. So you cannot really distinguish between electrons and the photons. So all we can say is that this nature of the access could be either electron-like or the photon-like, but we do not know which. So the question is to look for this access is that for the future experiments or the next experiments to probe this, should be able to separate the electrons from the photons with the new techniques or new detectors. But there is also additional thing we need to keep in mind, that the most recent result from the MiniBooNE did not only show this access in the low energy, but also they show that this access seems to be concentrated in this foregoing angle. So this is the events as a function of the cosine theta. So this is foregoing events, and you see that the access is pretty concentrated here. And this already is giving a scratch in our heads, because while this access coming from the low energy events would result in the foregoing angle, doesn't really make too much sense. But this is actually telling us that there is something more complicated than just the assuming neutrinos. There could be some different mixture of different models, or there could be very different phenomena that could be the culprit of this access that's showing up both in this energy and in the angle. And to understand this, now we have another question to answer on top of just separating the electrons and the photons. We want to understand all the different final states of the interactions in order to probe all the different possible scenarios or the models that could explain both the low energy access, also foregoing access. So the answer was to come up with the new advanced detector, which is the liquid argon time projection chamber, LARPPC in short. It has a long and rich history. It was originally, well, the basic idea originally started at 70s. So you can see that there are a series of the paper, one suggesting that they're using the liquid argon as the calorimeter with a lot of advantages. And second is just that using the time projection chamber as the 4 pi particle detector, also suggested at 1976. And finally, you combine these two ideas and come up with filling in the TPCs with the liquid argon. Then you can get just the good things from these two by with the obtaining the fine-grained 3D tracking with the energy deposition information in a very good resolution and fully active target without no dead space. And this is the principle of the liquid argon TPC. And this is actually a good representation of how MicroBooNE works as well on top of that. So here is how it works in a brief manner. There is a neutrino coming in. We cannot see the neutrino, but it interacts with the target medium inside of this liquid argon. And then first of all, it will prompt the scintillation photons from the argons. So that we can actually detect with the PMTs that we have installed at the same side of all these wires. So that's the scintillation light detection with the PMTs. We also have additional information, which is a charge information. So as the charged particle goes through the detector, it ionizes the electrons. And if we have the electric field inside of this TPC, then it will drift to these wires in this side, and we have these 3 different planes. And once the electron reach these dense wires, then you can have this how it looks like, and then we combine this charge signals, and then we come up with all this topology information as well as this energy information from these TPCs. So this is how it looks like in a real detector. There's incoming neutrinos, and this is the case of how the electron shower will behave with this cascade of the particles. And then attached, there is also track here. This is actually the proton track candidate. So you can see that with the RTPC have this great fine-grained 3D image with the great resolution, almost all continuously happening with the colorimetry information, as you can see from different colors representing different charge that we have detected in liquid argon TPC. So I said that earlier that there are these simply 2 paths that first we want to separate the electrons and the photons that the MiniBooNE could not do, or the Cherenkov detector could not do. So this is how we do it. First, we use the topological information. So the nature of the electron showers and the photon showers are different in a way that the photons has a gap between the interaction of the neutrinos to the beginning of the shower because of its conversion distance. However, electron shower is supposed to have attached vertex between neutrino interactions and the shower. So you can see that here is the attached vertex, where in this photon shower case, you have this gap between the shower vertex and neutrino vertex. So because of this great 3D imaging that we can have in the liquid argon TPC, we can look for this gap with a great precision. And this is one of the handles that we can use to separate electrons and the photons. The other, which is especially useful when you do not have attached track. When you have the attached track, then it's really easy to get this gap. But if there is no attached track, then it's hard to even reconstruct the neutrino vertex, and we could easily mistake that the shower vertex is the same as the neutrino vertex. Then what we should do is that we look for the energy deposition, or DQDX, at the beginning of the shower. And here, going back to the cartoon, because of the nature of the electron and the photon shower, there is the difference DQDX or DEDX, if you can calibrate it, difference between these electrons and the photon shower. You can see that there's just the one line of the electrons or positrons, where there's 2 of them in the photon showers because it's pair produced. So there's twice more energy deposited in the photon shower at the beginning than the electron showers. And this is how it actually looks like in real data. This is the dx, and you can see that there is a peak here at the 2 MeV per centimeter, and this is going to be the electron shower, where this one at this brown color events at the peak at the 4 is going to be our photon shower. So with these two handles, you can separate the electrons and the photons. But another question that we have to address is that not just separating the electrons and the photons, but can you also measure and reconstruct the other particles that comes out along with the electrons or the photons, which is, for example, protons, or maybe pions also, depending on what kind of interaction that neutrino goes through. And the MiniBooNE kind of case, they could not actually see this type of hadrons. They are actually only measuring the outcoming leptons. But with the liquid argon TPC, you can see that we are excellent at reconstructing this low energy, very short proton-like track, like you can see here. So this power of the liquid argon TPC to identify hadronic final states will give us more power to look into what kind of interaction the neutrino goes through, and eventually we'll be able to give us the power to look for what's the origin of the MiniBooNE access. So MicroBooNE. So I talked about liquid argon TPC, and MicroBooNE is the liquid argon TPC with the 85 tons of the liquid argon active volume. We have about 8,000 SEMS wires in 3 planes, and we have PMT to detect the scintillation photons as well. We have 32 of them. We also have the CRT, cosmic ray taggers, around our detector. This is particularly important for MicroBooNE. MicroBooNE is operating on surface, and because of that, we are suffering a lot from cosmic ray background. So it is actually important to tag the cosmic ray, or using any reconstruction or the event selection schemes to remove this cosmic ray background as much as possible. That I'll touch a little bit later. We are located at the Booster Neutrino Beam line at the Fermilab, which is the same beam that the MiniBooNE is located at. So we are the best suited for what the MiniBooNE anomaly by using the exactly same beam line as the MiniBooNE. And we've started taking data since October 2015. And the goal is that first of all, we are not the only liquid argon TPC in the neutrino physics. Actually, we are one of the first to taking the data with this new detector. There are a lot of other future liquid argon TPC experiments coming up, and especially, for example, like DUNE, which is our flagship US neutrino experiments, is also the liquid argon TPC. But because of it's a new aspect of it, we still do not understand completely or not well enough how the detector works, what's the systematics of it, what's the interaction between the neutrino and the argon nuclei look like. There are a lot of uncertainty of it. So one of the goals of the MicroBooNE is to look for, understand our detector better, understand how neutrino interact with the liquid argon better, and provide good inputs for the future experiments. But of course, our main goal is to address the MiniBooNE low energy access, and with this new technology. And I already told you the nice thing about liquid argon TPC. But talking about this, understanding the detector better, we have actually published many papers, and a lot of our earlier paper was regarding to understand this detector with a lot of data. So this is all the list of our publications from 2017 to pretty up to date. And you can see that we have a lot of papers on this detector physics with James, and also we recently started to produce a lot of physics research as well, including the cross-section measurement, but of course our recent research on low energy access. All right, so physics. The MicroBooNE's LE search analysis is now looking for these two photons and electrons. I've been talking about that a lot. And for the photons, which is, we call it a single photon analysis, is targeting at the NC delta radiated decay into the single photons. So this is the event display of those. You can see that this is the single photon without any protons. And here, this is a single photon with the protons attached at the neutrino vertex. This analysis has been published separately a little bit earlier, 2 weeks ago, and Giacomo and Lee gave an NPA talk last week about this analysis. And I'll come back to this at the, I'll show the result in the next slides. So this is the result of this looking for the single photons. So this is the cartoon of that, just the same as the event display that I showed you earlier. And this is the one beam analysis of looking at the data and the prediction. And you can see that and this yellow dashed curve is assuming that there is this low energy excess interpreted from the MiniBooNE to the MicroBooNE. And you can see that the data actually is preferring that the no LED prediction. So with this, we could reject the interpretation of the MiniBooNE anomalies with the single photons, or more specifically coming from this anti-delta radiated decay, and at the 94.8% contrast level. So I don't want to talk about this much because today's focus is looking for electrons. And for that, we are actually looking at many different final states. And because of we are using the PWTPC again, we can do this by looking at these different hadronic activities along with the electrons. So you can see that all these 4 different final states, you have these electrons in common, but along with that, you have 1 protons, 2 protons, no protons, or many other protons, or even other different type of the hadrons coming out. So why do we look for all these different type of the topologies? There are reasons for each one of them, and let me separate by these 3 of them here. First is the exclusively looking at the 2-body CCQE UV scattering, which is just the 1 electrons and 1 proton attached. The strength of this is that this is a very clean topology, and it's actually making our selection much easier and our purity much higher because it's much easier to select this type of events. But also CCQE interaction is what it dominates in the low energy. And remember, we want to look for the low energy excess. So being able to look, select only this CCQE or 1E, 1P selection will be giving us a good, better power of the selection, but also focusing on this low energy with a good understanding of the model, because CCQE is one of the cleanest, well understood in our neutrino interaction model. Second is what we call the semi-inclusive. So here we have 2 topologies. One is the electron with the multiple protons, more than 1 protons. And the other is just the electrons without any protons. So this is what we call 1E NP, and this is 1E 0P. And we are also trying to select without any pions. So there's a 0 pi also attached to it. The strength of this is that this is actually exactly what the MiniBooNE has been looking for. So by selecting these topologies, they are mimicking the MiniBooNE search for their signal. So this is the best suited for looking at, try to reproduce the MiniBooNE research as closely as possible. And finally, inclusive scattering. Here, this is basically, we just require we see the electrons and we don't really care about anything else. It could be 1 proton, no proton, any numbers of proton, or any numbers of the pions or other hadrons. So that's why it's 1EX. And the strength of this is multifold. And this is what I'm going to focus on this talk today, because this is what Yale Group has been involved in, and we've been contributing a lot on this specific topic. And the strength of it is that it's the less cross-section model dependent. Because it's inclusive, we have a lot of word data points. We understand it a lot. So when you compare the data to the model, it's not as depending on the model that we use, which we do not have the full understanding of. And also because we are not exclusive, this is topology agnostic. And because of that, we can achieve the high statistics and the high frequency selection if we come up with the nice, well-constructed algorithm. And finally, this type of the interaction is what the future experiment is going to look for, with the more high energy focus than the MicroBooNE, such as the dune. So this will be also great input for the future experiments, this type of research. And this is again a 1EX candidate data events with the electrons and the multiple hadrons defined. Before I go into the analysis further, I want to talk about what we are going to, once we observe the data, what we are going to compare that to against. We have our model, best understanding of how neutrino interacts, and based on free neutrinos, for example. But we also want to compare our data to what MiniBooNE observed. But MiniBooNE is MiniBooNE. How do we compare that in MicroBooNEs? So what we do is that we are unfolding the MiniBooNE's result under Louis hypothesis, basically coming from the electron neutrinos. But we are only considering in the energy space. So I showed you that there is also the access in the angle foregoing, but we are not considering that here. So we are only considering the energy dependence. And then we actually derive the scaling template to model this enhancement at the low energy of the intrinsic UV rate in the BMB, and then we apply it to the MicroBooNE just like this. And this is actually the simulated, the true energy of the neutrinos. So basically, we unfold this into our MicroBooNE simulation. And this is the case of the just taking this without just any normalization, that we also can test that we adjust this, allowing this normalization to float. That if it is 1, then it's just no nominal MiniBooNE. So whenever you see this x equals to 1 prediction, that's the nominal with the, this normalization factor just equals to 1. But we also test when you float this normalization factor and see what it best fits with our data later. So now we have this LEE model, then we can compare our data to our nominal prediction, or we can compare that to the ELE model prediction that takes into account the access that we have seen in the MiniBooNE unfolded into the MicroBooNE. So let's talk about how we reconstruct the our neutrino events in the liquid argon PPC with the specific reconstruction algorithm that we use in this inclusive search, and we call it the wire cell. It's too much to go into detail. It's very technical in the beginning, and then also a lot of mathematical tools going in, includes the boosted diffusion tree, XGBoost, the deep learning as well. So I can't go through each and every one of them, but I just wanted to say that our reconstruction is tied very closely together with our analysis. So for example, a certain type of other analysis may be using the reconstruction first and just using it as a tool to develop the event selection later. But here they are very much intertwined together. So our selection is actually appearing at the middle of this reconstruction and pattern recognition chain. So for example, our pre-selection, which is try to remove all the cosmic background rejection, is happening at this stage, not at the final stage. And our final event selection is happening after all of this has been implemented. So this is one of the interesting philosophy that wire cell analysis is using. But let me try to show you how the reconstruction works in a more visual way. We have 3 wires in PPC, and in each wire, we can record these 2D images. So these are the 2D images of the same set of events, and they are 60 degrees apart because each wires are 60 degrees away apart from the other planes. And the first goal is to how to stitch these 2D images together to construct the 3D image. And this is the video of kind of representing how it works. So you see this 2D image first, and then we slice them in the time with the time dimension. So this red slice is the time dimension, time slice. And you can see that for each time slice, we have these informations in the 2D. And then we do that for thousands of the time slices. And then we are using those information to stitch all these 2D slices together to construct the 3D image. So you can see that we are constructing this side by side, and finally we are coming up with this 3D image. You can see that we haven't done anything topology dependent thing yet. We do not know what topology. It does not really depending on topology at all. However, you do see that there are all sorts of different particles coming there. So we also want to separate them depending on what kind of particles they are, what kind of interactions they are. Once just that algorithm is done, you can see different colors are now representing different interaction, or we call it different clusters. And that is actually a big achievement from our 3D imaging. However, you do see also, this is really busy. Where is our neutrino? All these lines are mostly cosmic ray events, and one of all this cluster is neutrino. So in order to do that, now we need help from the PMT, or scintillation light. So what we do is that we look for observed PMT light patterns across all the PMTs and predicted light patterns. So you can see that these red circles are the PMT, observed PMT light, and the green is the predicted signal light. And we compare these two, and then that will give us the timestamp of each interaction. And with this timestamp and the help from the beam priming window, then we can finally come up with the neutrino candidate. And this is what we have found in this specific case. And you can see this familiar type of the neutrino interactions in the end. So with that, that's not the end. We just collected a cluster that looks like, or that's a neutrino candidate, but there are a lot more information that we have to grab from. First of all, we need to know if it is a shower-like or the track-like. So here we do the algorithm, and the red is shower, blue is track. And with that information, we also want to separate as many different particles as precise possible. So different colors are now representing different particles, but we do not know what particle it is yet. Now we use the energy information. You can see that these different colors representing different energy deposition, and that gives us both the particle ID capability. So here, these is the electrons and this is the protons with all this information. And finally, we use the deep learning technique to be able to select pinpoint where the interaction is happening. So it looks like it's really easy to guess from here to here, but because this is just a simple topology, with the very easy topology or low energy topology, getting this vertex right is pretty challenging. So we had to use this new deep learning technique to get this neutrino vertex, and finally stitching all this together, we can come up with all the information that we need.
Just a quick question. So the energy comes from the charge, the amount of charge?
Yes.
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 And is the deviation of the track from a straight line or any random meandering, is that also significant in identification? How straight the track is?
Yes, so there are algorithms to take care of that. If it is too much wiggling, then just topology cannot take care of it. It can actually scatter, like muon can scatters when it goes through the detector. So there is also separate algorithm to take care of that along with the energy. Yeah. So once that's now this is done, so we want to also estimate the energy. So we are basically, with all this particle ID information, we can just add up all this information that we have along with the charge information that we already know, and summing up different particles mass together. This is how the performance look like. This is the new case, and this is the unique case for the fully contained events. This is the first time I'm introducing the word fully contained. Fully contained means that it's the events with this cluster of the reconstructive activities that are entirely within the diffusion volume and not really exiting or touching outside of the diffusion volume. And this is a clean signal that we can look for. So for the fully contained UMCC events, you can see that for the reconstructing neutrino events on Y, true neutrino events energy on X from the simulation. You can compare that how our reconstruction is performed. And you can see a really nice well agreement with this resolution about 15 to 20%. And for the unique case, we have 10 to 15% resolution, also in a very nice agreement to the simulated energy. We also want to further calibrate this to get the as correct energy as possible. We do that separately for the track-like events and the shower-like events. For the track-like events, we do that with the DQDX information. So DQDX behavior between different particles like protons or the muons are very different. So this type of information also can give us more information to calibrate if our reconstructed energy from the track events are correct. But for the shower energy, instead we actually look to select the pi zero events. So pi zero events has a known invariant mass of 135 MeV. So once we select these pi0 events, both in charge current and neutral current direction, and we look for the peak of this invariant mass and see if it well aligns with our predicted value of 135 MeV. So after all the calibration is done, you can see that it's nicely well aligned, but also the data and the prediction also agree very well to each other. So these also give us some other information about our event selection is well done. So once we have all this information energies reconstructed, we now start with the selection. Like I said, our cosmic ray events is one of the most dominant background, and it's really hard to look them as we are on surface experiments with the long drift time of the liquid argon TPC. So we have all these tools from the wire cell, from the reconstruction and the pattern recognition, that we could actually remove 99.999% of the cosmic ray background rejection. And just to give you some idea, the ratio between the neutrino to the cosmic ray is initially 1 to 20K. So there are only 1 neutrino events per 20K cosmic ray events from the beginning. And after the pre-selection, we improved this to 5.2 to 1. So you can see how much powerful it was. But also it's not just removing background. We also want to keep neutrino as much as possible. If we lose all these neutrino events, then our efficiency is going to be too low. So we also try to keep this selection efficiency as much as possible. But after that, we are still left with a very small number of units because you are looking at MiniBooNE. Our electron-neutrino components is very small. So at this stage, we only have 0.4% of the electron-neutrino, which is our signal in our analysis. So of course, this is not done. This is just a pre-selection, but we start from there. And then after that, we use many different techniques to improve this further, especially the MUE. So we use the combination of the traditional tagging technique and the machine learning from the BDT and the XGBoost to do this selection. And you can see that this is the BDT score distribution of the mu and the ECC and the curves of the efficiency and the purity for both cases. And with our choice of the BDT score, our efficiency and the purity of the mu ECC is very high. For both of them are very high, 70 like to efficiency, more than 90 for purity. In the ECC case, 46% efficiency and 82% purity. So it's very pure. Efficiency is slightly lower, but it's still very amazing if you think about pre-selection stage. We only have about 0.4% purity, and we improved that to 82% purity. We're still keeping about 50% efficiency. So this is actually a big milestone for this analysis, to keeping this efficiency as high as possible, which is actually resulting in a very high efficiency and good exclusion power at the end of the analysis.
Okay.
Yes.
How do you define purity?
Sorry?
How do you define purity?
How do you define purity?
Yeah.
It's the number of these true neutrino events in the final selection to the all of them. So for example, this is actually a nice one. So this is a selected new ECC events, and this is a true new events, the green. And so among all the others, how much of these new events are there? That's the purity.
Okay, thank you.
So this is a spectrum, and I'm without any data yet, just the simulation. I'm showing you this because that you just want to show that how high statistics we have. For the new case, we have more than 100K events, predicted new events in this new case, and for the new case, we have more than 480 events. So we have now selection ready. Now we have to look for our signal. But before then, what we do is that in MicroBooNE as a whole, we try to constrain our signal, ECC here in this case, with our non-signal sideband samples. Why do we do that? That's because that we want to improve our understanding of the prediction model better with the other data that we can observe. But also because there are shared systematics between different signals and the other sideband, we can constrain our signals and decrease our systematic significantly. In our wire cell inclusive selection case, we use this so-called 7-channel selection. One is signal, ECC signal, fully contained, and rest 6 of the sidebands is used to constrain our signal samples. So for example, ECC but partially contained case, This is because it's partially contained and its resolution is bad. It's very less sensitive to the LEE. So if you look at this partially contained sample, there's almost no contribution coming from the LEE events. And this is serving as a control sample. For the MiniBooNE case, we have a very high statistics like you saw, and this is mainly used to constrain the flux and cross-section uncertainty of our signals. And finally, pi-not backgrounds, we have 3 of them, and they are used to constrain the background components in our signal samples. So this is how it looks like. This is our signal, fully contained UECC. This is partially contained UECC and MiniBooNE samples and pi-not samples. And all these sideband samples are used to constrain the UECC. But before doing that, we also need to check a few more things. That if our agreement between the data and the model prediction in the sidebands are consistent. If they are starts to be different, then we can't even constrain this, because constrain our signal sample is basically based on the assumption that our model prediction is consistent with our data in our sideband samples, and use that data information to get a better understanding of our signal samples. So here we also check that our data and our grids are very well with each other, but also very high statistics of this sideband helps a lot in constraining these our signal samples. Talking about the systematics, we have various different sources of these systematics, including flux and cross-section, but also the detector and the statistics. What you're seeing here is the relative uncertainty between all these different systematics components in these 7 channels, which is represented by different colors. The total systematics is in black line here, and this you can see that in our signal channels we have about 25% total systematics. But this is before constraints. Like I said earlier, after the constraints, these total systematics will decrease significantly, and I'll show that later. Now, this is the relative uncertainty between these different components to see that what component is dominating the most. You can see that the blue, this is the cross-section uncertainty, is the one of generally dominating. Again, this is before constraints. But also at the lower statistics region, like in this magenta line histograms, this is the detected systematic factor starts to dominate. So let me show you how the constraint actually worked in the end. So again, this is without any data. This is only our prediction, and you can also see that our LE is appearing at this low energy region, and this is our nominal prediction. This is our predicted total uncertainty. And then once we get the constraints from the sideband, and this is how it looks like. So I'll flip it. You can see the 2 changes. First, uncertainty. Like I said, uncertainty decreased a lot. This is more than a factor of 3, and this is the power of the using the constraints. But you are not seeing something different. That the prediction is also different. And that's correct. That after the constraint, the prediction actually increased a little bit from before constraints. And this is how we get a better understanding of our models coming from the sideband. Because our muon observation has a slightly access to the data, and that is actually correcting our prediction here through our understanding of our prediction from the muon sideband. So that's why it has increased a little bit more. So muon is actually driving this increase of our prediction a little bit in this low energy. All right, before showing you the final result, there are various validation processes, very long, very rigorous process before we are actually looking at the data in our signal regions. So one is that we look for different beamline data. So we use DMB data, same beamline as the MiniBooNE, but we also use the UNI beam, which also intersect to the MicroBooNE. So totally different beamline. And we use that to make sure that in our selection seems to be agreeing with our model prediction. This is a BDT score distribution. You see the data on topologies very well. And we also generate many different fake data or simulated data. Sometimes we inject fake LE signal, or sometimes we do not inject any LE signals, and we give that fake data to the analyzer without telling them what it actually is. And then analyzer take the data, analyze it, feed it through our event selection and full analysis chain, and then come up with an answer. If there is an LE, or if there is something wrong with the data, something is different, something is not agreeing to our models, all this type of the observation, and cross-check with actually how we generate those data. So for example, this case is one of those fake data sets. And this is also another type of the fake data sets without any LE injected actually. So that's why these fake data, these data points are all fake generated, and you can see that they agree with our prediction model. I already talked about this, that we also need to make sure all our sidebands, data and color need to agree well with each other. So we all look for the goodness of the fit for all these different channels, and these are the chi-square over NDF for before and after constraints, all giving you good agreement between data and Monte Carlo. And finally, even in our signal channel, our ECC fully contained signal channels, we just do not open up everything at once. We start from the high energy region where there is no LE, so you don't see this red dashed curve appearing in this highest energy, which is far sideband, and make sure our data and Monte Carlo agrees well with each other, no surprises. And then we open a little bit more. We start to see a little bit LE here. There is some fluctuation that we see, but still within our systematics. And then we finally open our signal region. Well, we already know the result, so there should be no drum roll needed for this. And this is the result. We open up our low energy region, and we found out that it agrees very well without the LE, just the nominal prediction. So zooming into this signal region a little bit more, only in this signal box channel below 600 MeV, we observe 56 events, and our prediction based on if there's no LE hypothesis, basically these are black lines without the red dash curve, we expect about 70 events. If we assume that there is an LE, which is this red dashed curve, then we should expect about 104 events. So you can compare that with the data, so you can naturally come up with the conclusion that the data agrees much better with no LE hypothesis than the LE hypothesis. And we have not found the excess of the low energy candidate events in our selection. Like I said, we now have this LE model and the nominal projection. So we compare our data to the fit with assuming that the no LE hypothesis is true or LE hypothesis is true, and do the simple delta chi-square analysis. And with that, we have found out that our data agrees with the no LE hypothesis at 0.45 sigma, so very good agreement. But and also this favors the LE hypothesis at 3.75 sigma significant level. So that is the inclusive analysis. Now I'll briefly show you what the other exclusive analysis has a result on, and if they're consistent with us. This is the two-body LCCQE 1E1P result. This is the cartoon, and this is their each selection. You see the prediction agrees pretty well with the data again here. So we exclude the ELE model with this 1E1P selection at 2.4 sigma. The other was the semi-inclusive 1E-NP and 1E0P without any pions in the final state. So they have two signals, topologies. 1E-NP case, you can also see that the data prefers no LE than the LE here. In the 0P case, it's just slightly different because we are actually seeing this small excess of the data points at the lowest energy beam. However, you also want to note that the 0P, 1E0P case, we don't actually have a lot of LEAs, and it's very low statistics if you compare with the other topologies. And it's not in a crazy disagreement with our prediction values. So with that, for the 1E-NP case, we exclude the LE model at close to 98% confidence level. And for the 1E0P case, it prefers the LE because of this small excess, but with more statistics, we may be able to look into this a little bit further. So this is all of them put together. And what we've accomplished is that we have developed these three different fully automated event reconstruction with the three distinct LE search analysis, both inclusive and exclusive, and they are consistent with each other. And this powerful imaging capability of the liquid gravity TPC that I keep emphasizing is the reason that we are being able to do this type of different selections. And this is when you compare the different topology result to another. So this is the data we observed with the uncertainty. This gray band is assuming there's no LE, and this red line is assuming the LE is there. And you can compare to our data to what model what it prefers to different models. You can see that the except for the case of the 1 in 0 p case, it all prefers the no-LE hypothesis. So that's the result, and I want to actually expand our view a little bit wider before I finish. What we have observed in this different topology is only few of all the different models that could explain the MiniBooNE anomalies. You can see that these are all the different models, and this is not all of them. This is only a part of them. And this is how this check marks is just showing you that the different topology can check these different models. And you can see that it's a long list of the models, and there are still a lot to explore. And using all these different topology in MicroBooNE, we're being able to check a lot of these different models. However, there are also a lot of different things that we still need to observe with our future data sets, or will be open a new door for the new physics of the different models, now that we have certainly crossed out a simple stellar neutrino model. And this is an example of all these different models. Again, this is not the exhaustive list, but you can get the idea that there are many theoretical models floating around to try to explain what the MiniBooNE anomaly is. And the MicroBooNE actually set the direction for all this. Now we need to look for, not for simple stellar neutrino picture, but something else. And again, I will emphasize for the last time, all this is possible because of our ability to detect the final hadronic state. If we couldn't do that, if we could only select the leptons, for example, then looking for different models is not possible. And our reconstruction technique and our detector, advanced detector techniques is the reason that we are able to probe all these many different models. I'll skip this, and this is our summary. So our results are found to be consistent with our nominal mu rate expectation from the BMB, and we did not see any excess of the mu events. And this favor this simple ELE model that was unfolded from the MiniBooNE case. So we can conclude from this that the mu cannot be the sole reason for the excess the MiniBooNE saw. And along with this photon explanation, that we can add another statement that this NC delta radiated decay cannot also be the reason for the excess that the MiniBooNE saw. And altogether, this is the first study of the MiniBooNE energy excess that appeared in a long time ago, 15 years ago. And this is, of course, not the end. Like I said at the few slides ago, there are many different models that we need to observe. Now, if it's not a simple stellar neutrino, there's a reason for this excess, then what could that be? And many models is actually pointing at a lot of exciting beyond the standard model phenomena. And we can actually try to look for that even further. We have twice more data statistics, including this one. And this more data statistics will also shed light on some of the features that we have saw. And along with that, this upcoming, or even some of the parts are running, this short baseline program of the Fermilab will also be able to help us identify what the MiniBooNE excess actually is. So that's everything. Thank you.
Okay. Very interesting talk. If you have a question here, just raise your hand, please. So,
I go first. Okay. Can you go back to slide 48? So I noticed that there is a underflow. Sorry, 47 maybe. Yeah. So it seems that there is a under fluctuation around 600 MeV. It was not evident to me if it was that's true in the other analysis as well. But is there any explanation to what that could be? Yeah, I'm not sure if that's true for the other analysis, the under fluctuation, but it happens in the analysis that you're talking about. Is there an explanation for that?
The best explanation right now is just the statistical fluctuation, and we have many reasons to believe that. We look for, I didn't show any here, but you can look for our paper for different kinematic variables of these selected events, and there is no indication that this type of the deficit is appearing at a localized parameters. So this is what we believe. We believe that this is more or less to be a statistical fluctuation, but the more data to come. So hopefully they will be able to resolve this. Yeah, we don't believe this is with any particular reason.
And that happens with the form analysis, or?
Well, yes and no. For example, you may be able to see a similar feature here if it's one NP case.
Yeah.
But it's not as clear in the one in 1P case, even though it's generally kind of under fluctuating, but not as similar as the these two cases. One in 0P case, we don't see any. So it's a mix. It's a conclusion at this point.
Thank you.
We have a question online. So, Sid, do you want to go ahead?
Okay. How should I compare your result now with the improved constraints on stereo-neutrino mixing that you had in Minos, Diabay, and the Boogie 3, I guess if I'm pronouncing it right, that came out in 2020, the Adamson PRL, which claimed to exclude the earlier result. How do I compare the strength of your result and their result in the other system?
You can't do that yet. We haven't done that yet. We are, so the all the result that I show you here today is just solely trying to see if where the access of the MiniBooNE is coming from. To fit this into the global stereo-neutrino picture, we will probably have to do another set of analysis with a much more careful study. But what we are showing here isn't tuned to that. So right now you cannot really directly compare our result to those fit yet.
Okay.
Yeah, I guess I just had a follow up on that. So the p-values on the goodness of fit here you were showing were like 10%, maybe on, I saw that 10 to 20% on a couple different plots, and I completely agree. It's probably going to go away as you have more data, but should I interpret all those p-values are correlated? I mean, if you have another fluctuation in one, I know these are all somewhat inclusive select. You know, the last one has the same events as some of the others. Should I be thinking of those p-values as pretty correlated?
So we have an additional study coming up. We have actually combined all of this, looking for overlapping events, taking into account all of this correlation between different selection. It's coming up, so I can't say right now, but there is a third correlation. But right now, what I can say is that they are all currently the preliminary result is showing all the consistent result across all these different selections.
And the global p-value, when you take all the other fluctuations together, is also in the 10, or I guess maybe you're going to show this, but
Yeah,
it's not, you know, shockingly low, I guess.
it's not showing.
Maybe a quick question. Why only 1/2 of the data?
Why? Well, it takes a long time to
Okay.
process the data.
That's it.
So we have this half of the data still under production, and it requires a lot of computation power. So that's the reason.